Thank you. So the concept of prodrug is very important. It means administration of the drug in a masked manner. So a non-active compound is administered, and then after metabolization we have the active drug. In this way, we can avoid particular problems related to bioavailability. For example, low absorption of acids, free acids, because they are ionized in charged form. They lose a proton, and so they have a negative charge. Alcohols, polyalcohols, they are hydrophilic, and so it's very difficult their absorption. In addition, you know, acids normally are poorly tolerated because they are irritant. There are specific drugs administered by injection, and they have an acidic function, and they are poorly tolerated because the injection can cause strong pain. Otherwise, if we take a free acid orally, we can have problems with the irritation of the intestinal tract, intestinal cells, parietal cells. And finally, a drug can have unsuitable organoleptic characteristic. Normally, it's a lot of drugs are bitter and repulsive. So it's very difficult to assume this type of drug orally. If possible, we can transform these bitter acids in esters. In this case, esters are not soluble in the saliva, on the tongue, and so they cannot interact with the taste receptors. So we can avoid the interaction of bitter acids with the taste receptors located on our tongue. Here you can see two important examples of prodrugs, and we'll see these two prodrugs during the course. First of all, a classical example of bitter acids is represented by chloramphenicol. You see this molecule. It's an important antibacterial, the first antibacterial synthesized industrially. And so it was possible during the 50s to have tons of this compound by synthesis, chemical synthesis. It was a very potent antibiotic, but after the general use in the population, we had some resistant strains, and so now it is used only topically, drops near the, no more orally. The problem of this molecule is its taste. It's very, very bitter. And the idea was to mask the one alcoholic function, you see here, this oxygen atom, with an ester of a bicarboxylic acid, you see, in order to decrease its water solubility and to avoid the interaction of chloramphenicol with taste receptors. After its assumption orally in the stomach, in the intestine tract, there are the esterases are present, and so these enzymes can hydrolyze and release the free active form of chloramphenicol. You see here the hydrolysis of this ester group, and we get again the free OH group. The second example is L-DOPA. We have already discussed about this prodrug. L-DOPA is a precursor, a biological precursor of dopamine. The biosynthesis of dopamine, the pathway of the biosynthesis, starts from tyrosine, and the second step is represented by L-DOPA. Dopamine is necessary, it's important in the CNS to control the fine movements. And so, if the dopaminergic receptors die, it is necessary to replace, to increase the presence of dopamine in the CNS, but it's not possible to assume to use dopamine directly because dopamine is too hydrophilic, because dopamine and physiological pH is protonated, and so it is no more, it's not able to cross the blood-brain barrier. But if we use L-DOPA, you see there is a carboxylic group and an aminic group, so it's like an amino acid. L-DOPA can use a particular transport system present in the blood-brain barrier, can cross the BBB. After that, there are, in the CNS, it's present DOPA decarboxylases, this particular enzyme, able to transform L-DOPA in dopamine. We lose carbonic anhydride, okay. Decarboxylation. So these are two important examples of prodrugs. But we'll see during the course other examples. The last slide of this part is reserved to the human gut microbiota. You know that in our intestine there are a huge number of different microorganisms, very useful to transform all chemicals, and they are important to increase absorption of particulate. Yes? Ciao. Come stai? Ok, ci vediamo dopo. Ciao. And this microbiota is very important to increase the absorption of particular benefic compounds, natural compounds. So there are a lot of food supplements that we can take to increase, to protect our microbiota during perhaps the therapy with an antibiotic. It is important to preserve our microbiota, and so we can take some food supplements during this specific therapy or during our life. Okay. So we have finished the phase 1 reaction with these slides, and then yeah, please.
Concerning the N-DOPA, and so when it is had after its metabolization, CO2 is released.
Yeah.
Does that
It's a gas, you know.
Yes, but it released inside our brain.
Yes, but the concentration is too low, and so no toxic. Okay, not toxic effects at all. Yeah. It's very, very low concentration, and then normally carbonic anhydride is toxic, but you know, it's transported away from the sites very fast. Okay, so now we start with some examples of metabolic biotransformations. Yes, okay. So you can see where and how our enzymes transform particular molecules. It is not important that you know the chemical structure of these compounds, because we'll see all these different classes of drugs during the course. The first molecule is a very old molecule called meprobamate. Is an hypnotic, very old. You see, one of the metabolites found in the urine is the hydroxylated derivative. And so our metabolism is able to introduce an alcoholic group on this carbon atom. A second example is quinine. Quinine is an antimalaric drug. Cinchona succirubra. Perhaps, do you remember the plant? And you see,
the drug from Cinchona?
Succirubra. Is it right? Because have you studied this during the botany, no?
I remember Cinchona. I don't think.
Succirubra, okay.
I don't think.
Yeah?
It was.
No?
Officinalis.
For me, Cinchona, yes. Because I remember from my more than 35 years ago. Just a moment. Cinchona succirubra. Yes, I think so. Yes, succirubra. Yes, it's right. The cortex of this plant is very useful for you, because we can make a gene, you know. Gene, Schweppes. Inside the Schweppes you can find the Cinchona succirubra cortex extract, okay. Because they was discovered by English troops in India, and they try to fight the mosquitoes, to fight the disease from mosquito, to have an anti-malaric activity. Yes. So one of the metabolite, once again, an OH group from the aromatic ring. Another example is chlorpromazine, antipsychotic, antischizophrenic. You see an nitrogen oxide, an oxidation of the nitrogen atom. And another example, we have already seen this type of example, phenacetin. You see the metabolite is paracetamol. Paracetamol is a tachypirina. So paracetamol is the active ingredient released by our metabolism. Diazepam is an anxiolytic. It belongs to the family of benzodiazepines. We'll see this family. These drugs are very used and very common, but not diazepam, because diazepam has a shelf life too long. When you take one tablet of diazepam in the evening, the day after you have a strong effect on the CNS, and so perhaps you remain, you sleep again, you continue to sleep. It's like a post-drunk sensation. Okay. So it's not so. It's not a good sensation. And so the scientists investigate the metabolites of this drug, and they found in the urine this hydroxylated metabolite called oxazepam. Oxazepam is the last active metabolite of diazepam. This means that the shelf life of oxazepam is not too long, only 3 hours. So you can take oxazepam in the evening. After 3 hours, you have the effect. You can stay in your bedroom for 80 hours. And then the day after, you are fresh. You are relaxed. This justifies the success of oxazepam. Now the commercial name is Tavor. It's I think one of the most sold anxiolytic drug in pharmacy. This means that metabolism can represent also a source of new drugs, because we can investigate the metabolites, we can identify new active metabolites, perhaps with better pharmacokinetic properties.
No, can you repeat this idea, please?
Please?
Can you repeat this idea?
Yeah, okay. It is important to investigate also the metabolite, the different metabolites of a drug, because sometimes you can optimize the pharmacokinetic properties of a specific drug. In this case, you have diazepam with a useful activity but too long. And if you want to limit the duration of activity, you can assume the last metabolite, which is easily eliminated, and so you have a shorter period of activity. Is it clear?
Yes, thank you.
Okay. So you are here an example of chlorpromazine, and you can see the whole site of metabolization. Aromatic hydroxylation, sulfur oxidation, nitrogen demethylation, nitrogen oxidation. So when an exogenous molecule arrives inside our body, all different enzymes can attack together to transform, in order to transform the molecule in a more hydrophilic compound.
So all of these reactions can happen
Simultaneously, yes.
oh,
Yeah.
and only one compound and then I will take
Yeah.
not many compounds.
No, a lot of compounds you
A lot of
obtain.
compounds.
Yeah, really. In urine, it's possible to find 10, 11, 12, 20, yes. And it is necessary to identify each of them when you prepare your request to the health agency. For every drug, it is necessary to know each metabolite. Ooh. Okay. Here you can see the same example in Spanish. Okay. I found this slide in Spanish. And here you can see also the phase 2 reaction. We'll see now the next chapter, the conjugation with the glucuronic acid, but we'll see later. Once again, diazepam, you see the different metabolites, and we'll see this example in particular during the description of a drug for CNS. Phase 2 reactions. So, phase 1, transformation. Phase 2, conjugation. We put together our drug or a metabolite of our drug with other compounds, backbone, to increase normally the hydrophilicity of these metabolites. Because I remember you, the aim of the metabolization is to increase the elimination of exogenous compounds. So, phase 2 reactions involve the transfer of polar groups into the substrate molecules with the formation of a covalent bond. Substrate, co-substrate, active fragments, and enzymes are involved, so we put all together. The most important reaction of phase 2 is glucurono-conjugation. The conjugation with glucuronic acid. Why glucuronic acid? Because it derives from glucose, and glucose is very common in our body. And glucose is a very hydrophilic molecule. Oh, where is the phone? Just a moment. Yeah?
I don't remember from yesterday. Phase 2 reactions follow phase 1 reaction?
No,
or
all
either one or
together.
the other?
All together.
Simultaneously?
Yes, yes.
But they always happen for a drug, both of them?
Yeah.
So depending on the functional group, a drug undergoes one or more phase 1 reactions, but always phase 2.
Yes. Okay, normally you see here, in the urine you can find everything. You see this example, diazepam, you can find the hydroxylated metabolites, but also the glucuronic derivative, you see? Sometimes you find a mixture of the different metabolites and glucuronic acid derivatives. The aim is to maximize the elimination of the drug. This is the main goal of the metabolism. So the problem is we have to transfer a polar group on the drug to the drug backbone. This means that we have to activate the glucuronic acid. This reaction requires a lot of energy. And so it is necessary to have the active form of glucuronic acid. How we can activate? You know, from biochemistry, ATP, ADP are activated form of energy. In this case also you can see the bond between the glucuronic acid activated with the uridine diphosphate. So we have a high energy bond, and this bond can be attacked by a nucleophile, X. X is a nucleophilic group, O minus, S minus, nitrogen, organic acids, charge minus with the minus charge. So Rx is our metabolite, and this metabolite is, or drug directly, is able to attack the electrophilic point, the activated glucuronic acid, in order to have the formation of a new covalent bond, high energy bond. This means that glucuronic acid derivatives are very stable. They cannot be hydrolyzed. So they remain after their formation. They are stable. You see on the top the chemical formula of glucose. You see the OH group on the carbon 5. And in glucuronic acid, this OH group is oxidized to carboxylic acid. So glucuronic acid is a derivative of glucose. But why glucuronic acid is so hydrophilic? Because there are a lot of OH group from glucose, okay, but there is also an acidic group that can be ionized, so it's charged. So this final molecule, the glucuronic acid conjugate, is very hydrophilic and can be eliminated very, very fastly, very easily. Here you can see some example on morphine. Perhaps you remember that morphine is a natural alkaloid, a very potent painkiller, able to cross very easily the blood-brain barrier. And here you can find the two different glucuronides found in the urines of patients. The first residue of glucuronic acids is attached on the oxygen, on the phenolic oxygen atom in 3 positions, 1, 2, 3. You see morphine, 3 glucuronide. And the second example, you see the glucuronic residues is attached to the alcoholic oxygen in 6 position. The first glucuronide is easily eliminated. An exception, we find an exception with the morphine 6 glucuronide because this compound is a potent agonist, is still active and can interact with the morphine receptors. It has an anomalous lipophilicity caused by the particular conformation of glucuronate. Perhaps the molecule in solution assume a different conformation in which the glucuronic group is masked by the backbone of morphine. And so this type of glucuronide is still active and can interact with the receptor. Other examples, just to understand how this process works. Once again, chloramphenicol. You have already seen this type of antibacterial drug. You see the conjugation with the glucuronic acid on this OH group, alcoholic group. Phenoprofen is an anti-inflammatory. Once again, you can see the interaction of this acidic group with the glucuronic acids. We have an ester in this case. Sulfamides, in this case, this is an acidic proton, so the nitrogen atom can assume a negative charge. And here you can see this negative nitrogen charge can interact with the active form of glucuronic acid. Carbon glucuronides. Here there is an acidic proton that you don't see, but you see the carbon has 4 bonds. Here there is a hydrogen proton. This hydrogen can be lost. We have a minus charge in this point. This minus carbon atom can interact with activated glucuronic acid form to get the glucuronic derivative. Possible sites of glucuronization. Amide, uncommon, hydroxylamine, sulfonamide, amine, tertiary amine, and thiol, you see. So these are a summary about of possible sites of glucuronization. Once again, oxygen glucuronization, acyl glucuronization, you see here on the acidic group. Nitrogen glucuronization, this nitrogen is a nucleophilic atom able to attack the activated glucuronic acid, and so we get this, the glucuronic derivative. So these are examples just to explain you how this process works. Second reaction of phase 2. Conjugation with an acetyl residue. In biochemistry, we have already seen acetyl coenzyme A. It's a very important structural building block, because from acetyl coenzyme A starts the synthesis of a lot of compounds, cholesterol, fatty acids, and so on. And these residues can be transported on the molecule of different drugs. Also in this case, X is a nucleophilic group present on your drug. And this nucleophilic group atom is able to attack the activated acetyl coenzyme A to get the acetyl derivative. So we have an acetylation of the drug. Here you have an example, very simple. Sulfanilamide is an example of a very old class of antibacterial drug. We have two different sites of acetylation. One is on this anilinic nitrogen atom. You see the nitrogen atom is directly located on an aromatic ring. We have an aniline. In this case, you see the acetylation of this nitrogen. So we have an amide in this case, no more an amine. Amide. The second site is represented by the second nitrogen atom, very close to the sulfur atom. And in this case, the behavior of this amino group is different. It's not a basic group, it's an acidic group. This NH2 can lose a proton. We have a N-. This N- is able to interact with the acetyl coenzyme A in activated form to get the acetyl derivative. So these are two examples of acetylation of different sites of the same molecule. Sulfate conjugation. Conjugation with a residue of a sulfuric acid. Sulfuric acid is one of the most strong inorganic acids. You remember? H2SO4 is a very potent acid. This means that the residue of these acids is ionized at every pH value in our body. For sure at 7.4, but also in the stomach. It's a very strong acid. Yes, in this case, we have the second dissociation. You remember, no? Two different dissociations. The first, more acidic, and the second one, less. But, however, these residues remain the residue of a very strong inorganic acid. Also, in this case, you have a nucleophilic group present on your drug, able to attack the activated form of the sulfuric acid. In this case, we get the conjugated derivative. So in this, you see this example, estrone. Estrone is an hormone, a female hormone. In this case, we have a conjugated compound with a strong acidic residue present on the backbone. This means that this conjugated compound can be easily eliminated. So this is the strategy of our body. How to eliminate as soon as possible exogenous compound by migration of a very polar group on the backbone, on the bicovalent bond. Yes. Phenols, alcohols, sulfate conjugate, you see. Amine also sulfate conjugate. Conjugation with glutathione. We have already discussed about this interesting compound, natural compound. You can see the chemical structure of glutathione here. Glutathione is formed by 3 natural amino acids. Glutamic acids, very simple, here you see. Cysteine, you see the thiol group is peculiar of these amino acids, natural amino acids. And finally, glutamic acid. So glycine, the first one, cysteine, the second, and glutamic acid, the last one. 3 simple amino acids. This compound is a strong nucleophile. Why? The thiol group, SH, can be easily ionized at physiological pH 7.4. We have as S minus 4. You know that the sulfur atom has a lot of electrons. And in this case, S minus is a strong nucleophile. This strong nucleophile can very easily interact with an electrophilic compound. And so we get the conjugated of glutathione with your drug. So we get the glutathione conjugated. This is the first step of the reaction. After that, this glutathione conjugated can lose the residues of the glutamic acid. And we get this basic, the residues of the glutamic acid, you see? This is the residues of glutamic acids can be lost. In this case, we unmask, yes, the function of a free amine. After that, the third step, we can lose the glycine residue, and we get an amino acid derivative, you see, because you have a free amino function and a free acidic function. The last step consists on acetylation of the amino group to mask this compound and to get only a free acid. This last compound is called mercapturic acid conjugated. Mercapturic because the residue of the free acid with the sulfur atom is called mercapturic acid. Two important points. Glutathione is a strong nucleophile. This means that glutathione can react with all electrophilic species present in our body from exogenous sources.
But it's a nucleophile, right?
Can?
It's a nucleophile.
It's a nucleophile, yes, because you have a S minus, a lot of electrons, no? This means that when we introduce toxic compounds, because they are electrophilic and they can attack our DNA and our cells, can be attacked. In this case, glutathione can protect our cells from the attack of electrophilic species, free radical species, because you know that free radicals needs electrons. They want to complete the electron orbitals. So we have to protect ourselves with glutathione. So glutathione, you can find glutathione in a food supplement, in a cosmetic creams and so on, because it's a very important protective agent. But also in this case, you can see how a glutathione is able to increase the polarity of a electrophilic species to eliminate this toxic compound. Yeah.
At the beginning of the speech, you said that the important things were two.
Sorry.
At the beginning of the speech, you said that the important things were two.
Okay, yes, okay, bravo. Yes, the first one was to protect, and the second one is because it is able to eliminate a toxic compound in this by this pathway. Yes, yes, these are the two things. Thanks. Here you have an important example how glutathione can work to protect ourselves. This compound is called etacrinic acid. Acid, you see the acidic function here. The chemical structure is very simple, looks like. But this compound is very potent. One of the most potent diuretic. Do you know the meaning of diuretic? It is able to increase a lot the volume of urines because it is able to block the absorption in the kidney. It reacts with the particular transport system, particular enzymes present in the kidneys. How it reacts? You see this special group, a ketone, okay, normal. Alpha beta unsaturated ketone. Alpha beta, two carbon atoms very close to the ketone function, alpha and beta. Normally, you know the polarization of a carbonate compound. Oxygen is delta minus, carbon is delta plus. But in this case, we have alpha beta unsaturated carbon atom very close to the ketone group. And you see here Oh, I am not able to concentrate. Voice is terrible. You can see the form of this alpha beta ketone, unsaturated ketone. And so you can see the plus charge is now on this carbon atom, no more on the ketone function. And this is the site where your nucleophile, for example, this glutathione, can attack to give a covalent bond on this carbon atom. You see here the system, alpha beta unsaturated ketone. You have a minus charge in this point because there is a acidic proton here between two ketones. The minus carbon is able to attack on this beta carbon, and then you have the formation of the covalent bond. Okay, protonation, and then you get this is the final compound. So the tetracrinic acids can be attacked by glutathione, yes, but also by nucleophilic groups present on the surface of particular enzymes in the kidney. In this case, you block the activity, the active site of these enzymes, and you block the reabsorption of water in the ansa di Henle ansa. Do you remember the kidney? There is a specific, I don't know if it's here, no, okay, we'll see, but we'll see later. There is a particular point in the kidneys where the water is reabsorbed again to reduce the volume of urine. You see the final product when glutathione attack this drug, you see, the sulfuratom. But the glutathione reserve in our cell can finish. And after that, this compound can react with enzymes, with the DNA, and so on. Is it clear? Yeah. Have you seen during the organic course this type of reaction? Oh, nice. Perfect. Once again, do you remember the metabolism of benzene ring with the formation of the epoxide? And so glutathione is able to attack this very reactive compound. Also in this case, alpha beta unsaturated ketone, sulfonates. So, last reaction of phase 2. Methylation. Methylation is a very simple reaction. We have seen big groups transported, migrated on our molecules. In this case, only a methyl group, very small. But this simple reaction is able to stop the activity of particular neurotransmitters. The enzyme, the class of enzymes involved in this reaction is called methyltransferase. Once again, we have an activated methyl group, S-adenosylmethionine, you see. And this activated methyl group can interact with a lot of nucleophilic compounds, alcoholic groups, amine, and so on. You see the positive charge on the sulfur atom, so in this case we have an electrophilic activated derivative that can be attacked by nucleophilic groups. The example is noradrenaline. Noradrenaline, you know, is a very potent neurotransmitter inside our body, CNS, adrenergic system. It's very important. Noradrenaline is active in our heart. It is able to increase the frequency, the contraction, and so on. But when noradrenaline is released in the synaptic cleft, yes, it can react, it can interact with the postsynaptic receptors, but after seconds, minutes, its activity should be stopped. How? With a simple methylation of one of the two OH alcoholic phenolic groups present on aromatic ring. The name of this enzyme is catechol, C, O for oxygen, methyl for the group transferase. Catechol or methyl transferase. This enzyme is able to transfer a methyl group on the oxygen of the catechol ring. And so the final product is this methylated noradrenaline inactive. So this simple reaction is able to block the activity of one of the most potent neurotransmitters in our body. Okay. Have you any questions? Okay. So I think we can stop for 15 minutes now. 11:05, I think about 11:20. Okay, we start again. Okay, and then we have expression and go on. Okay, now mangio un cioccolatino e mi devo andare. Okay. Allora, okay. That was my colleague. Okay. So, excretion. We have already seen how our body is able to change, to increase the hydrophilicity, and now we see how the molecules can be excreted by mainly by kidneys. Main routes of excretion, you see, renal, biliary, and pulmonary. Secondary excretion routes, lacrimal, sudoral, salivary, milk. Child, okay, but are not so important, these are second routes. Renal excretion. You can see in the picture the structure of the nephron. Nephron is the main unit of kidneys. And in this unit, there is a excretion of particular polar compounds. But also lipophilic compounds can be reabsorbed again. So we'll see what happens in the kidneys. There are several processes. And all these processes contribute to the elimination of the metabolites. In particular, we have two important processes, glomerular filtration and tubular secretion. Glomerular filtration is a passive excretion. It depends only by a gradient of concentration. And you can see that all plasma solutes pass through, including drug, except those bound to plasma proteins. Yes, only the free drugs are able, only the free metabolites are able to be filtrated at the glomerular level. Tubular secretion is an active process. It requires energy because there are specific transport systems able to bind metabolites, hydrophilic substances, and to transport these hydrophilic substances directly to the urine. It is necessary, this type of process, because sometimes we have toxic charged compounds, and these compounds are not able to cross the membranes at the kidneys level, and so it is necessary to have a specific transport system able to take these anionic and cationic compounds and transport them inside the urine. These are saturable systems, you know, and competitive systems. Here you have a complete picture about what happens inside the kidneys. Absorption, orally, gastric intestine, liver, metabolization, metabolites, and here you see what happens inside the kidneys. Elimination of hydrophilic metabolite in urine, so glomerular filtration, metabolite secretion, and there is a third process called passive reabsorption. If during the glomerular filtration you have the elimination of lipophilic compounds, these compounds can be reabsorbed again in the blood because they are lipophilic. And so at kidneys level, we have three main processes. Glomerular filtration, passive, and it depends on the gradients, concentration. Active secretion, number 2. And number 3, passive reabsorption of lipophilic xenobiotic. Reabsorption. No, excretion. There are particular transport systems able to eliminate polar compounds. You have here an example with the benzylpenicillin. Benzylpenicillin is one of the first penicillins as antibiotics, old antibiotics. You see that this benzylpenicillin is characterized by an acidic group here. So it is an acidic compound. And this compound normally is ionized and can be eliminated by active secretion. There is a specific transport system able to take the acidic compounds and to eliminate these acidic compounds into the urines. We can use, in association with the benzylpenicillin, this probenecid. You see, it is another acidic species And probenecid competes with the same transport system of benzylpenicillin. So probenecid is able to interact with the transport system, and probenecid is eliminated, but benzylpenicillin remain on the blood. So we can prolong the shelf life of benzylpenicillin by association of this drug with the probenecid. Probenecid is able to interact with the acidic transport system in kidney. Please.
Are they two different drugs or in the same tablet?
On the same tablet, yes. It's an association. Probenecid is also a forbidden compound as in doping. Why? Because if probenecid is found on the urines of athletes, this means that you want to mask something. Because probenecid is able to block the elimination of a lot of acidic compounds. Benzylpenicillin is one of them, but also is able to block the elimination of other acidic compounds. And this means that you take probenecid, you want to mask the elimination of other doping compounds used in doping. There is a special list of the forbidden compounds, and one of them is probenecid. Tubular reabsorption, filtration, elimination inside the urine. But if your compound is lipophilic, this compound can be reabsorbed again. So perhaps it could be a positive point for a drug, but sometimes we see it's not so good. It depends from the pKa of your compound, from the log P. And in particular, it is important to know the pH of urines. Normally, the pH of urines is about 5.5. And so we have to know the behavior of ionizable compounds to know if at this level your compounds can be reabsorbed or not. You see the urinary pH 5.5 to 7. We can change the pH of urines by using weak acids, for example, ascorbic acids, vitamin C. If you assume vitamin C, you can have an acidic pH of the urine, or we can assume weak base like sodium bicarbonate, and so we can have almost basic urines pH 7. In this way, we can control the reabsorption of ionizable compounds. You see here in the picture the behavior of an acidic compound. For example, ibuprofen. Ibuprofen is a painkiller, you know. It has an acidic function, COOH. And so if you want to have the reabsorption of this compound at urinary level, we have to maintain the pH about 5. Because at 5 you have a very low concentration of ionized form. Very low concentration of CO minus. Almost form of the free acid, COOH. In this case, we have free acidic form, and in this way, this form can be reabsorbed. I can control the pH of urine in this case by assume ascorbic acid or other weak acid. On the contrary, if you want to eliminate an acidic species very fastly, you have to increase the pH of urines about 7 by using weak base, sodium carbonate, sodium bicarbonate. In this way, we have a high concentration of CO minus. The compound is in the ionized form, and in this form it is difficult its reabsorption. So, low pH value of urine, we have strong reabsorption of acidic drugs. Strong absorption of acidic drugs, but low absorption of basic drugs because they are protonated. Basic pH in the urine, low absorption of acidic drugs, high reabsorption of basic drugs. So we have two pH units. We can control the pH of the urine inside this small window. No, it's not so small. 2 pH units from 5 to 7. In this window, we can decide which kind of compounds can be reabsorbed or not.
So,
Yeah.
I have a question. When the pH is around 5, you have low concentration of what? Of free acid or free base?
No, okay. pH 5, you are in acidic condition.
Okay.
You are an acidic drug. In this condition, the acidic drug is ionized and so easily reabsorbed. Okay? On the contrary, a basic drug, it's protonated in a protonated form, and so it's not reabsorbed. Okay? At 5 pH unit. At 7, the situation is the contrary. At 7, an acidic drug is ionized, with the charge, is in a charged form, and so it's not possible its reabsorption. On the contrary, a basic drug is unionized, is not charged, and so it's possible its reabsorption. It's clear?
Yes.
Okay. There is an interesting compound, an interesting example related to uric acid. You see the chemical structure here of uric acid. Uric acid derives from the metabolism of adenine. When we eat a lot of meat, you know, there are the DNA inside the cells, and we eat a lot of DNA bases. the metabolism of adenine, the last compound, is the uric acid. Normally, uric acids can be additional metabolized in order to destroy its backbone. But in some people lack of this type of enzymes. So they have a high concentration of uric acid inside the blood. What happens? Uric acid is not so soluble in blood. It can crystallize in the foot fingers, for example. You see the urate crystals here, and you are in this. These people have strong pain, strong inflammation, the inability to use the foot finger, to walk, and so on. But why they crystallize? Because you know the crystals are heavy, and so they go on the feet, and so they crystallize in this part, in the feet, and then in the legs, and they can block the movements. Because uric acid is reabsorbed at kidney level, because it is a useful compound, can be metabolized to give energy and so on. But in some people they lack this type of enzymes, and so they have a high concentration of uric acid. How we can eliminate this type of acid? To drink a lot of water, first of all. If you see on television, if you drink a lot of water, you make a lot of urine. With a bird, you say, on the television. But another strategy is to block the reabsorption of uric acid using, in this case, sulfenpyrazole. You see this compound. Sulfenpyrazole is able to interact with the reabsorption system, and so uric acid remains in the urine, and we can eliminate from the body, we can restore the foot finger movements and so on.
Also with the diet, it's possible to prevent the deposition.
Please?
With the diet, we can prevent.
Yes, okay, yes. You have to avoid the meat, fish, only vegetables, but you know, sometimes we need the proteins. This is the main problem. Okay, you can eat soybean, I know, but sometimes we need fresh meat. But in this case, if you take sulfenpyrazole, you have a strong results. Yes.
The sulfenpyrazole interact with what?
Please.
The sulfenpyrazole
Yes.
interact with what?
Yes, it's able to interact with the reabsorption system, and so uric acid remains in the urine. So we have seen the elimination by kidneys, and then we see the second type of excretion from the liver by bile acid. What happens when we assume a drug orally? This drug is absorbed in a gastric tract, intestine tract. All drugs is transported to the liver, and here this compound can be mixed, can be conjugated with the bile compounds. There are specific surfactants inside the bile secretion. And the bile secretion goes to the intestine. In the intestine, you can have again a free drug. We can be reabsorbed again. We can be complexed again with bile and then return to the intestine. You see, it's like a circle. Enterohepatic circulation. At the end, your drug remains in the intestine and can be eliminated by fecal elimination. So bile is important. Bile is important because you see the two main components, cholic acid and glycocholic acid. These two acids act as a surfactant. You know what is a surfactant? Surfactant please.
To decrease the surface tension.
Yeah. They have a polar head normally and a lipophilic tail, and so they are able to solubilize lipophilic compounds, because normally with the diet we eat a lot of fats, and it is difficult to absorb this type of molecule, and they have to remain in solution, you know. And cholic and glycocholic acids are very important for the digestion. These two compounds are able to complex, to form a complex with our drugs, and can facilitate the absorption, the intestinal absorption of fatty drugs. So some drugs can be absorbed in the intestinal tract, and then they go to the liver and they are eliminated with the bile inside the intestine. This is the pathway. Pulmonary excretion. Normally, we can eliminate by this way the volatile compounds, such ethanol. You know, when policemen stop you and they check the level of ethanol in the blood, they check the ethanol in your lung. And in this way, ethanol is eliminated. General anesthetics, we'll see, it's a special chapter of our program. Chloroform, the volatile compounds. And so minor excretion routes, you see, lacrimal, milk in the child, and so on, but these are really no important for us. So, extent and rate of bioavailability. These are two important concepts, rate and extent. We have already seen something about the absorption of a compound, you know, able to reach the active concentration in the blood or not. This is almost the same rate. We can absorb a compound very fastly. And so we have a high peak, perhaps with a lot of side effects. Or we can have an absorption during the time very slow. This compound is absorbed very slowly. And so this compound is not able to reach the active concentration. But first of all, it is important to remember the first pass elimination. This means that if we take a compound orally, normally 60% of this compound is metabolized by liver. And so only 40% can remain to give the therapeutic effect. And this compound can be also excreted in the bile. You see, we have already described this process. Okay. Now I show you a movie about like a summary of the different points that we have treated in these last two lessons. Okay, so you have seen also how aspirin works. It is able to block the pain, to block the inflammation, but we'll see next chapter this type of compounds. So you have seen, however, the whole process that implies absorption, metabolism, elimination, distribution, and elimination. Okay. So have you any questions? No? At home? Any questions? No? Piyush? Jude? No? Okay.
It's all clear, Prof. Thank you.
Okay. Okay. So now our drug is distributed. Now our drug can reach the target. And we are so in the pharmacodynamic phase. Pharmacokinetics phase is related to the distribution of our drug inside our body. The pharmacodynamic phase implies the interaction with the target, specific target. This target can be classified in two different types. Specific receptor, these normally are specific proteins where your drug can interact, can modify the quaternary structure of these proteins, can activate specific receptors. And in this case, we need a particular chemical structure of the drug in order to have an optimal interaction with these specific targets. There is another class of targets called generic binding site. Why generic? Because in this case, it's not requested a particular chemical structure, but only particular chemical physical properties. For example, a lot of compounds are volatile, ethanol, and other esters. And these volatile compounds are able to interact with the neurons and to block the transmission of pain. These compounds are normally used in general anesthesia, and they will see this particular chapter, and they block the transmission along the axon of the neurons, but with a very generic process. And this is an heterogeneous class of compounds. All these compounds have in common the property to be volatile. So in this case, we say a generic binding site. Probably they interact with the membranes of neurons, and they are able to disorganize the structure of the neuron membranes. And at this class belong a very low number of compounds. Most of compounds interact with the specific receptors, and so they need a specific chemical structure. However, specific receptor or generic binding site, at the end of the interaction, we have the effect.
So
Yeah.
the generic binding site, you said that they interact with the membrane of the neurons.
Yeah, yeah.
And then
Yes, they disorganize the structure of the membranes of the neurons, and so it's difficult the transmission, the pain transmission. Probably they interact with the phospholipidic chain, long chain, and they block the channel, they close the channel, the ionic channels. This is an hypothesis, but all of these volatile compounds have the same activity to block the pain transmission. Okay. So we can say that we can have structurally specific drugs which interact with the specific receptors, and in this case it requests a specific chemical structure. Or we can have structurally non-specific drugs, and this is the case. Different chemical structures, but same activity. Here you can see a deeper description of these two different types of drug. Structurally specific drugs, their spatial structure is critical and fundamental in determining the drug dynamic phase in order to have the therapeutic effect. Important properties include the stereochemistry, electronic properties. In general, their action is mediated by a receptor, okay. And at this class belong a lot of compounds. The most compound, normally the most of drugs used in medicine. Structurally non-specific drugs, the structure does not play a critical role in determining the pharmacodynamic phase, for which the physicochemical properties of the drugs in the biophase are important. Their action is general, depression, the neurotransmission, you know, and not linked to specific receptors. We start from this last family because it's not so important. Just to underline that normally all these compounds have the same chemical physical properties. Normally they are volatile, they are eliminated by pulmonary way, and we can assume by directly in gas form. At this class belong only the general anesthetics, so it's a very limited class. More important is the second class. Yes?
General anesthetic, the structurally non-specific drugs are only general anesthetics.
Yeah. Anti-disinfectants, but you know it's very general. You can have an antibacterial effect on the skin by different chemical structure. Normally they act as surfactant on the bacteria, so they can disorganize the cell wall of the bacteria, but it's a very general property. Okay. The most important class is the first one, yes. And in this case, we have to consider the biological macromolecules as drug targets. In particular, we can have two different groups of biological targets. Nucleic acids, DNA, RNA, and so on, and proteins, enzymes, ionic channels, ionic pumps, carriers, and so on. In this case, the problem is related to know the chemical structure of the target. It is not possible to have a snapshot, to have a picture of the target. It's not possible. And so it's not so easy to design new drugs for specific targets if we don't know the chemical structure of these targets. Here you can see an example of a molecule called doxorubicin able to interact with the DNA. You see the double helixes of the DNA, the Watson and Crick model, you remember? And you can see that doxorubicin is able to stay between the two helixes. In this way, they can block the reading of the two helixes during the replication phase, because doxorubicin is an obstacle, can block the enzymes which try to read and to synthesize the additional chain, DNA chain. This molecule, doxorubicin, is an anti-cancer, and we'll see this compound, will meet this compound in the class of the anti-cancer compound. They are called intercalators because they are able to stay between the two DNA helices. But in this case, we know the chemical structure of the target because we know the chemical structure of the DNA. So it's quite easy to design a drug able to interact with this target because we know its chemical structure. Also, messenger RNA can be considered a drug target. For example, we can synthesize antisense RNA, a complementary chain, RNA chain, able to block the messenger RNA. In this case, we block the synthesis of particular proteins. Otherwise, messenger RNA can be considered a drug. You know the history about the vaccine against COVID. Messenger RNA is a drug. The scientists were able to stabilize these chemical structures and to use these compounds as drugs. Another example of a drug target can be represented by ionic pumps. You know that in our stomach we have a pH value about 1.5, 2. This means that it is necessary to have a high concentration of protons, and this is possible because in the gastric cells there are a particular pump transport system able to take the protons and to release the protons inside the stomach. In some cases, it is important to block this pump in case of gastric diseases. And there are specific compounds, you see here, omeprazole, pantoprazole, and so on. These compounds are able to block this pump. And so in this case, the pH of the stomach can reach level about 5 to preserve the parietal cells of the stomach, to protect. Here, yes?
But then, how can the stomach carry out digesting the pH?
Yes, this is the problem. During the treatment with this compound, you can protect your cells, your gastric cells, but you can have some problems related to the digestion of the foods. Because, you know, it is important to have an acidic condition in stomach to eliminate the most part of bacteria from the food. And so also it is important, the acidic media, to have the optimal activity of the different digestive enzymes. In this case, you can preserve the gastric cells. Perhaps there are ulceration, you know, other type of problems. And so we have to protect gastric reflux. If you want to avoid this gastric reflux, we can control the pH of the stomach. Here you can see a series of painkiller compounds, diclofenac, mefenamic acid, and so on. All these compounds are able to block the pain, yes. But the most severe side effect of these painkiller compounds is related to the inhibition of the formation of the preservative mucus, protecting mucus inside the stomach. This means that when I take ibuprofen, for example, these compounds inhibit particular pathways that we see, and this compound blocks the biosynthesis of the protective mucus inside the stomach. So the protons can attack the parietal cells, can destroy part of the wall of the stomach. So if we want to preserve our stomach, for example, if we have to take this compound for a long time, because you have a particular strong pain, so we have to take this compound for a long time, it is necessary to protect gastric cells by using drugs able to block the ionic pumps. So in association, we can take diclofenac or ibuprofen or other painkiller together with pumps inhibitors such as omeprazole, pantoprazole, lansoprazole, and so on. Yeah?
A friend of mine told me that when she takes painkillers, she always throws up.
What?
Vomit.
Ah, okay.
This could be a side effect of what you said.
Yeah. Ionic pumps are important, yes. We can block them, yes. But also, I remember once again that there are also extrusion drug pump. We see the pump from another point of view, from the inner part of the cell. And these pumps are able to take our drugs and transport them outside the cell. But also in this case, we can use multi-drug resistant extrusion drug pump inhibitor. So once again, we can inhibit ionic pumps, okay, if we want to control the stomach pH level, okay. But also we can use inhibitors of the extrusion pump. Here in the picture, you have an example. Anti-cancer drug, anti-neoplastic drug. This drug is able to reach the cancer cells. This drug is able to enter inside the cells, okay, to give its toxic activity against the cancer cell, okay. But the cancer cell has a special extrusion system. In particular, this system is called the P-glycoprotein. And your drug is transported outside again, outside the cell. We can use an association, an inhibitor of this type of pump, and in this case, your drug can remain inside the cell. So we have seen, just a general consideration, we have seen a lot of transport systems. Important, yes. Inwards, but also outwards, the cell. Really, some years ago, we wrote a special chapter on this topic, and really there are a lot of different transport systems in the intestine tract. And so the situation is not so easy. because a lot of foods can interact with the transport system and can block the absorption of a lot of drugs. Now, we have the last point of today. Enzymes. Just a moment. Enzymes can represent the ideal biological target. Why? Because it is possible to crystallize this type of protein. Just a moment, yes. This means that you can have a snapshot, a picture of their structures. This means that with specific softwares, we can design specific inhibitors of enzymes. Here in the picture, you can see the structure of a particular enzyme called acetylcholinesterase. This enzyme is present in the synaptic cleft, and this enzyme is able to hydrolyze acetylcholine. Here you see the mechanism, you see the acetylcholine, serine and glutamate interaction with the acetylcholine, water, hydrolysis. This is the mechanism of the hydrolysis of acetylcholine. This means that it's very easy to design specific inhibitors of these enzymes to block the hydrolysis of acetylcholine, and in this way we can increase the concentration of acetylcholine inside the synaptic cleft. But when we need a high concentration of acetylcholine, when we want a strong activation, for example, of neurons. In case of Alzheimer's disease, when very few neurons remain active, we can counteract this disease by increasing the acetylcholine concentration in order to increase the activity of the low neurons present inside the brain. Most of drugs used for Alzheimer's treatment are inhibitors of acetylcholinesterase. But the neurons remain died. So it is not possible to restore neurons, the number of neurons inside the brain. We try to increase the activity of the low number of neurons present by increasing the concentration of acetylcholine.
There is a possibility that the few neurons that remain will also die.
Ah, yes. Because we don't know. Yes, we don't know Yeah, the etiology of the disease. We don't know.
Are we increasing the amount of neurotransmitter produced, or we are increasing its permanence in the synaptic cleft?
No. Okay. We are inside the synaptic cleft, and so we increase the concentration of acetylcholine inside the synaptic cleft. Yeah. But you know there is a the structure of synaptic cleft. You have the neurons, and then presynaptic and postsynaptic receptors. And so if we have a high concentration of acetylcholine, we can increase, we hope to increase the activation on the postsynaptic receptors. Yes. Due to the facility to have a picture, a structure of enzymes, normally the research of the companies, the different research of the companies are concentrated to find molecules that interact with enzymes. It's easier to investigate, to design new molecule for enzymes. More difficult is to design molecule for receptors, we'll see. Because the receptors, it is not possible to crystallize the receptor proteins. And so if you want to have a result in a very short period, we have to know the chemical structure of the target. We design specific molecules, and then we can have a new drug in very short time. How it is possible to make a picture of the enzyme? By X-ray investigation. It's possible to have a crystal of the enzyme, or particular enzyme. We put this crystal under the X-ray equipment, and we can obtain this type of structure. Because the X-ray interact with the atoms inside the crystals, and so we can have information about the different type of atoms inside the enzymes. The main difficulty is to have the right crystal. But after that, in 1 week, you can have the structure of a particular enzyme. On the web, you can find a lot of chemical structure of the different enzymes. So it's possible to download their structure if you want to see, to design new drugs, to design new ligands, and so on. More difficult is to design molecule able to interact with the receptors. Why? Because the proteins, because the receptors are located normally in the cell membranes. And the chemical structure of the different receptors is stabilized by the phospholipid layers. So if we try to extrapolate this protein from its environment, we lose the tertiary, or quaternary structure of this protein. And the result is that we have only a simple series of the different amino acids. So you have a chain, a linear chain of the different amino acids. But we have no idea about their arrangement in the space. So we don't know the tertiary or quaternary structure of a protein when we extrapolate this protein from the matrix of the membrane. This is the main problem, to find new drug able to interact with the receptors. Do you understand this point? So enzymes are very simple to investigate. You have a snapshot, you have a picture. For the proteins, for the receptors, it's not so easy. There are specific molecules able to activate particular receptors. These molecules are called agonists. For example, we have already discussed a lot about acetylcholine. Okay, acetylcholine is a neurotransmitter, is able to interact with the postsynaptic receptors, yes. Is able to activate these receptors, yes. In the case, for example, of Alzheimer's disease, we need a stronger molecule able to activate the postsynaptic receptors, and in this case, we say that we have a new agonist. An agonist is a molecule able to activate the receptor in the same way that the neurotransmitter. So an agonist has the same activity of an endogenous neurotransmitter. Okay.
But both the neurotransmitter and the drug bind to the receptor, or in the presence of the drug, since the drug, for example, has high affinity, only the drug binds to the receptor?
Neurotransmitter and drug, in this case, they go to the same receptor. But if you want to potentiate the activity of acetylcholine, we can use more potent agonists.
Well,
Yeah.
I didn't understand what you mean when you said that agonists have the same activity of the endogenous neurotransmitter.
Yes, they are the same.
Like, well,
Yes, Alzheimer's disease.
okay.
Only 2 neurons remains in the brain, for example. We want to have a strong activation of these 2 neurons, and the acetylcholine present in the synaptic cleft is not enough. We can use a stronger agonist, and then we can potentiate the activity of acetylcholine with this drug.
Okay.
Okay?
So the effect is additive or synergistic?
Additive. And normally they compete for the same site. But you know there are a lot of different examples, allosteric site and so on, okay, but the situation is not so simple, but however, we can say that. Okay, have you any questions at home? No? No more questions? Okay, so we'll see next time, on Thursday, okay? in the morning, and then we start from this important point to design molecules for the receptor. Okay? Okay.